We will explore the electric force. This is the type of force that acts between charged particles. It can be repulsive or attractive depending on the nature of interacting charges. The law of charges states that like charges repel and unlike charges attract. This force is calculated using the formula F sub E is equal to the products of constant K times the magnitude of charge sub 1 and magnitude of charge sub 2 divided by R raised to the power of 2. This formula or law tells us that the larger the magnitude of the interacting charges, the stronger the force will be. The smaller is the distance of separation, the stronger will be the force. The magnitude of the electrical force is directly proportional to the magnitude of the charges and inversely proportional to the square of the distance that separates them. The electric field. How do charges know where the other charges are located? The electric force is distributed over an area. It shares the properties of electric force acting over it, making it an electric field. Strength of the electric field. This is the amount of electric force acting over a charge. The formula for the electric field E is equal to F sub E, the electric force, divided by the magnitude of the charge, Q. This depends on the absolute magnitude of the charge and the distance at which the test charge is placed. Work done by an electric field. The electric field can move or affect charges in its vicinity. Hence the electric field can do work on charges. Work is defined as the product of force and displacement. We also know that the formula for the electric field E is F sub E over charge Q. We can simplify this and we will see that it is equal to K times Q over R squared. And therefore we see that the electric force, F sub E, is equal to electric field E times charge Q. So the amount of work done by the electric field on the charge is computed by substituting this expression for F. We find that work W is equal to the product of charge Q times the electric field E times the displacement. We now define voltage. Voltage is the amount of work done per unit charge. We have voltage V is equal to work W over charge Q. We have a formula for the work done and this is equal to the electric force F multiplied by the displacement D divided by the charge Q. We also know that F sub E is equal to the electric field E times charge Q. When substituted to the formula we find that voltage V is equal to the product of electric field E and the displacement D. We can try to formulate an equation to count charges. We should recall that particles have charges that is either positive or negative. Electrons have negative charge. It has a magnitude of negative 1.6 times 10 raised to the negative 19 coulombs. The mass of the electron is 9.1 times 10 raised to the negative 31 kilogram. The proton has a positive charge and it has a magnitude of 1.6 times 10 raised to the negative 19 coulombs. The mass of the proton is 1.6 times 10 raised to the negative 27 kilogram. The total number of charges is an integral multiples of the basic magnitude of charge times n. We have a formula for Q which is equal to n times E. Electric current. Streams of electrons that are moving. Electrons are more mobile compared to protons. Electric current is defined as the number of charges that passes through a given point per unit time. We have current I is equal to Q over T. The unit is ampere in the honor of a scientist named André-Marie Ampere. It is also equivalent to charges that pass through a given point per second. 1 ampere is equal to 1 coulomb per second. We can now discuss the movement of the electrons. Electrons move in random direction. The resulting electric field ensures that there is a net displacement. As we can see in this diagram, the length of this conductor is delta x, which is equal to the drift velocity of the electron and the change in time delta t. The total number of electrons in this conductor is related to its concentration per unit volume. Volume of this conductor is V, is equal to area A, times the drift velocity, times delta t. We can see that the total number of electrons inside the conductor at any given time is equal to Q, which is equal to N times V. This is equal to N times Q times A, multiplied by the drift velocity, and delta t. We see that if the number of charges changes per unit change in time, the current in the conductor is given by I, is equal to delta Q over delta T. This is equal to N times Q times A times the drift velocity V sub D. We can try to find the electric current per cross-sectional area. The current per cross-sectional area is called current density J. It has a formula, current density J is equal to μ over A. We will see that current density J is equal to N times Q times the drift velocity V sub D. The units for the current density J is equal to amperes per square meter. We can also explore the relationship of current density J to resistivity. We find that current density J largely depends on the magnitude of the electric field. Different materials reacts differently to electric field. In metals, the current density J is directly proportional to E. This relationship is called the Ohm's law. Discovered by the German physicist George Simon Ohm, 1787 to 1854, in 1826. We define the resistivity ρ of a material as the ratio of the magnitudes of electric field and current density. We have a formula for the resistivity ρ is equal to E over J. The electric field E is found using the equation ρ times current density J. We know that energy is lost during collisions. If we have a conductor with uniform cross-sectional area and uniform length L, and we apply an electric field, charges will react to the field and a potential difference will develop at the ends of the conductor. Charges tends to flow from higher voltage region to lower voltage region. The energy possessed by the charges is gradually lost because of numerous collisions. From the previous definition of current and voltage, we can see that voltage V is equal to E times L, where L is the length of the conductor and current I is equal to current density J times A. Solving for E and J gives us E is equal to V over L, and J is equal to I over A. We can substitute this to the equation of resistivity and find the amount of resistance in a circuit. We can see that the resistivity ρ is equal to V times A over I times L. We cross-multiply L and A to the resistivity and find out that ρ times the ratio of length L over area A is equal to V over I, which is equal to the resistance R. This is also the formula for the Ohm's law. R symbolizes the resistance in the circuit. Resistivity ρ has unique values for each material. We see that the resistance increases as there is also an increase in the length of the conductor. We shall also see that the resistance decreases if the cross-sectional area of the conductor is also increased. The formula for the Ohm's law is resistance R is equal to V over I. We can now try to compute for the power in the circuit. Power is defined as the rate energy is delivered or converted per unit time. This is also defined as the amount of work done per unit time. The formula for power is P is equal to energy E over delta T, which is also equal to work W over delta T. The unit of power is called watt, in the honor James Watt. We can use the definition of voltage to find the amount of work done per unit charge. We see that the change in work denoted by delta W is equal to delta V times the charge Q. Substituting this to the equation of power, we find out that power P is equal to delta V times delta Q over delta T. This is equal to power P is equal to V times I, or P is equal to I squared R. Welcome to the university. In this video we will discuss the three types of electrical circuits. We will also teach you how to solve for total resistance in a series connection, including the ways on how to solve for the total resistance in a parallel connection, how to solve for the total resistance in a series parallel connection, and how to solve for any electrical quantity in simple electrical circuits. A basic circuit has three main parts: a source of energy, also known as voltage source, a closed path or conductors for the current to flow, and a device which uses the energy, also referred to as electrical load. If any part of the circuit is open or missing, the device will not work. There are ways to wire circuits. There are two basic ways to wire a circuit. The other method is just the combination of a series and parallel connection. Before we introduce the ways to wire a circuit, keep in mind that a resistor could be anything, for example bulb, toaster, ceramic material, and other materials. Resistance. The first type of circuit connection is called a series connection, in which resistors are connected one after another. This is sometimes called the head-to-tail connection. The second type is called the parallel connection. You will see that in between a set of junctions, resistors are connected parallel to each other. All heads are connected and all tails are connected at one end of each junction. When studying electrical circuits, one must be familiar with the electrical symbols used in making circuit schematic diagrams. We introduce some basic but very important symbols used in circuit analysis. Schematic symbols. Before you begin to understand circuits, you need to be able to draw what they look like using a set of standard symbols understood anywhere in the world. For the battery symbol, the long line is considered to be the positive terminal and the short line denotes the negative terminal of the battery. You also need to familiarize yourself with the measuring apparatus or monitoring device used in circuit analysis. We introduce the voltmeter and ammeter. They are special devices you place in or around the circuit to measure the voltage and current. The voltmeter and ammeter. The voltmeter and ammeter cannot be just placed anywhere in the circuit. They must be used according to their definition. Since a voltmeter measures voltage, or potential difference, it must be placed across the device you want to measure. That way you can measure the change in voltage across the device. Voltmeter is drawn or connected across the resistor. Since the ammeter measures the current or flow, it must be placed in such a way that it can sense the flow of charges. It is connected in series where the charges go through the device. Current goes through the ammeter. Simple circuit. When you are drawing a circuit, it may be a wise thing to start by drawing the battery first, then follow along the closed loop starting with positive and drawing the symbols of your circuit elements until they form a closed path back to the negative terminal of your battery. You can see such a diagram below. We will now explore series circuits. In a series circuit, the resistors are wired one after another. Since they are all part of the same loop, they each experience the same amount of current. In the figure, however, you see that they all exist between the terminals of the battery, meaning they share the same potential difference generated at the end of the terminal of the battery. It is also true if we say they share the same voltage. We see that there is no other way for electrons to pass through, and they must pass through each resistor. Hence we can say that the current in the series circuit is the same across every resistor. We say that I sub t is equal to I sub 1, is also equal to I sub 2, and is also equal to I sub 3, and so on and so forth. As the current goes through the circuit, the charges must use energy to get through the resistor. So each individual resistor will get its own individual potential voltage. We call this voltage drop. Using Ohm's law, this voltage drop is equal to V is equal to I times R. We sum up all the individual voltage drop across each resistor to get the total voltage, V sub t. So we have V sub t is equal to V sub 1 plus B sub 2 plus B sub 3, and so on and so forth. This is also equal to V sub t is equal to I times R sub 1, plus I times R sub 2, plus I times R sub 3, and so on and so forth. We know that we have a constant current flowing in a series circuit, and therefore we can factor it out. We will have V sub t is equal to I times the quantity of R sub 1 plus R sub 2 plus R sub 3, and so on and so forth. We have the formula for the total voltage in a series circuit is equal to I times the summation of all the resistance, or I times R total. We also found out that the total resistance in a series circuit is equal to the sum of the individual resistance present in the circuit. Note, they may use the terms effective or equivalent to mean total. We now try to apply the concepts that we have learned. See the sample below. A series circuit is shown to the left. We add the individual value of each resistor and we will get 6 ohms. What is the total current flowing in the circuit? We apply the formula I is equal to V divided by R, and we will get 2 amperes. Since we know that in the series circuit, the current is constant through all the resistors. What is the voltage drop across each resistor? For this question we apply Ohm's law to each resistor separately. We will see that the voltage drop across R1 is 2 volts, for R2 is 6 volts, for R3 is 4 volts. Notice that the individual voltage drops add up to the total. We now discuss parallel circuits. In a parallel circuit, we have multiple loops. So the current splits up among the loops with the individual loop currents adding to the total current. The voltage across every resistor in a parallel circuit is the same as that of the voltage source. It is important to understand that parallel circuits will all have some position where the current splits and comes back together. We call these junctions. The current going into a junction will always equal the current going out of a junction. The amount of current flowing in a junction is equal to the amount of current flowing out of the junction. In a parallel circuit, we notice that the junctions both touch the positive and negative terminals of the battery. That means you have the same potential difference down each individual branch of the parallel circuit. This means that the individual voltage drops are equal. We have the formula V total for a parallel circuit is constant and is equal to V sub 1 is equal to V sub 2 and is equal to V sub 3, and so on and so forth. We also notice that the current is different across each resistor. We can sum it up to find the total current. We can use the Ohm's law to get the current in each resistor. We will find out that the total current is equal to I sub 1 plus I sub 2 plus I sub 3, and so on and so forth. Using the Ohm's law to show that the total current in a parallel circuit is also equal to the total voltage, V sub T divided by the total resistance R sub T, and this is also equal to V sub 1 over R sub 1, plus V sub 2 over R sub 2, plus V sub 3 over R sub 3, and so on and so forth. And then we use the fact that the voltage is just equal across each junction, and hence we can factor it out. We can now use this to find the total resistance in the circuit by dividing both sides of the equation by V sub T. Notice that this is in its reciprocal form. We can now apply these concepts in the sample problem below. To the left is an example of a parallel circuit. A. What is the total resistance? When we apply the formula and solve for the reciprocal of 1 over R sub T, we will see that it is equal to 2.20 ohms. The next question is, what is the total current flowing in the circuit? We use the formula for the Ohm's law. V is equal to I times R, and we will see that the current is 3.64 amperes. What is the voltage across each resistor? It is 8 volts each. We can also try to find the current in each resistor. We apply the Ohm's law individually to each resistor and find out that the currents are 1.6 amperes, 1.14 amperes, and 0.9 amperes for R1, R2, and R3 respectively. Also note that individual current adds up to the total current. We can also combine series and parallel circuits to make a compound, otherwise known as complex circuits. Many times you will have series and parallel in the same circuit. See the example below. Solve this type of circuit from the inside out. What is the total resistance? We will try to simplify the complex parallel circuit and find out the equivalent resistance that can be added to a series circuit. We will see that the circuit above is also equal to the circuit below. We just have to add the values of the resistance, and we will see that it is equal to 113.3 ohms. And we can also find out more about the circuit. Thanks for watching. See you again here in the university.